Okay. Hi, I'm E from University of Southampton. In today's presentation, I'll talk about one of the research activities happened in our group, focusing on the development of the water-activated textile battery. Today's presentation, I'll go through this bullet point, starting with the motivation, then the background of the water-activated batteries, and the pathway of how we achieve, including testing result and the video to demonstrate the battery to power up the LEDs. In conclusion, I will mainly talk about the near future development and plans to enhance this battery on textiles with performance and also packaging. E-textiles started from the very right-hand side by attaching the conventional electronic component, and after a long effort, it has been achieved by depositing the material directly onto the textiles. But however, the textile battery is still needed to power up these functionalities. Water-activated battery can be considered as a reserve battery, where the water is the only missing element in the water-activated batteries. And once the water is added externally, it will trigger the releasing of the stored energy within the two electrodes through the combination of the salt layers. And the benefit is it can be stored stably for a very long time with a negligible self-discharging rate. And the application of it, because of the benefit, it can be used for the emergency power supply, and the power supplies for the disposable applications, as it's a very low cost to build these batteries. And the key applications is it could be used as a passive cell power sensing application for the humidity and leak detections for the logistics of parcels while in transport. And this is the theory behind the water-activated batteries. And these are the 5 layers with 2 electrodes on top and bottom, and 3 salt layers in between. But in actual fabrication, the middle of the sodium nitrate layers need to be at least 10% wider to minimize the leakage current in the battery, while after adding the waters. And that's a simple oxidation reduction reactions. This slide is about the fabrication of the water-activated batteries on textiles. We have tried all these 4 process options, which they all work, but some of them need more look into the formulation to fit the deposition techniques requirement in the rheology of the inks. And I presented today the result is based on the deep coating. And by doing this research, we've been through the 3 textile options with all different features behind it. The woven cotton textile is the pure natural fiber, and polyester cotton is the most widely used textile nowadays, and it has synthetic and the natural fibers twisted. And the woven silk textiles represent the thin textile as a carrier of the batteries. And in actual testing, we use the switch lock to hose and compress the 5 functional layers. And this is a schematic drawing of the switch lock. Later on in the conclusion, this slide is showing the test result of the discharging test of the water-active battery on textiles under the condition of -5 milliamp per centimeter squared. And it has some very interesting figure, shows the energy stored within the two electrodes. And this is the video to demonstrate its ability to power up LEDs. So that's it. We've made two actually in series to increase the voltage output. And conclusions, based on this research activity so far, we've achieved a water-active battery on the textile with the ability to power up the LEDs. And the novelty of it is we can use solution process to add the battery function onto the textiles, but at the moment we can only do it with a relatively thick porous natural fiber, which is option 1 textile, the woven cotton textile 100%. But for the polyester cotton, we found out the polyester will be damaged partially by the acid of the one of the acid layers, the salt from in between the electrode. And for the silk one, it's too thin, so the current will go through without any control. And that's why we've proposed this future work. It's ongoing work, actually. The process investigation will aim to reduce the number of the textile layers in the battery. Ultimately, we try to realize the battery on the single textile sheet. And then we plan to increase the energy storage by changing the two electrode within the battery to increase the voltage potential across the two metal plates. The last is the most important, is we are looking into the investigation of realizing the forming technology of a porous membrane within the textiles. So with this technology, we can actually add the water-active functional battery into any textiles, including the polyester cotton and the silk, where this membrane will protect the synthetic fiber and also increase the difficulty of passing the current through, for example, silk. And then with this, we can increase performance of the textile and also broaden the textile options by to deploy this water-active battery. Okay, thank you very much. Thank you.
Thanks very much. Thank you. And questions? I have one. Maybe so. In terms of plans to increase the energy storage, can you comment on the role of why you want to replace the aluminum and the silver electrode? How do you plan to do that?
That will be from the second point of the ongoing work. We will look into other metals where we have the ability to turn it into printable paste. And then there's a oxidation and the reduction table for the metals. The wider they separate from each other, the higher voltage potential you can output. Yeah. But for this feasibility study, we get the aluminum and the silver, which is off-shelf commercially available paste.
Maybe another question. Have you observed any degradation mechanisms? I mean, on top of you mentioned the effect of the acid, right?
Yeah.
Have you observed any other degradation mechanisms related, for instance, to cycling of the battery after a few cycles? So on and on.
We haven't get to that far at the moment, and this is a primary battery. It doesn't get recharged.
Yeah.
Okay. Thank you. Thank you.
Thanks very much. Thank you. Uzoma Odua or Olufemi Lori in the room? No? Then, okay, I think we can close the session for today. coffee break, and we will convene at 4 with the last session.